Okay, hopefully you built yourself a non-inverting amplifier and you worked your way through quiz 2. So let's take a look at quiz 2. So we've got the difference amplifier. The difference amplifier is defined as an amplifier that subtracts two inputs and multiplies it by a gain. Typically, we try to have the gain as high as possible because we're going to use that gain in negative feedback to correct for errors within the op-amp. Has a fairly high input impedance, which means that it takes very little current. Low output impedance. Now, that output impedance is not necessarily zero. It might be a couple hundred ohms. But once we add negative feedback, that output impedance is reduced by the gain of the op-amp, and for all intents and purposes, it's zero. It's in the milliohm range. And since our op-amps can't put out huge amounts of current, we don't worry too much about a small voltage drop across a very small resistor. So, our op-amp rules are no current flows into or out of the inputs of a perfect op-amp. In is 0. By the way, when I talk about the input current to the op-amp, you don't know whether it flows into or out of that terminal. It could be either one. The current's so small we don't worry about it, but don't assume it's a current into versus a current out of. That very much depends on how they build the op-amp. If there's negative feedback, that's underlined because that's the first step you should take when analyzing an op-amp circuit is make sure there's negative feedback. If there isn't negative feedback, then the output is A times V plus minus V minus, which almost always means the output's either at VCC or VEE. The op-amp keeps the negative input at the same voltage as the positive input when there's negative feedback, so you can assume that V minus equals V plus. That is only true if we keep the inputs less than VCC and more than VEE. And in fact, that's for a perfect op-amp. As we'll see in the next lesson, we may actually need to be further away from the power supplies for it to work properly. The output of the op-amp can never be greater than VCC or less than VEE. That should be sort of obvious just on what we know about electronics. There's no real way to get more voltage out of something. At least you don't know how to do it yet. If we apply 15 volts and minus 15 volts to a circuit, we expect the output to be between minus 15 volts and plus 15 volts. All right, so apply the golden rules to design a non-inverting amplifier. We're going to use an LF411 and standard value resistors. We want a gain of 100. We don't know what the output impedance of our signal source is, and we've got plus minus 15 volt supply. Well, I'm always going to start by drawing my 5-terminal device. Since I've got 15 volt supplies, that's what I'm going to use. It's an LF411. I want a gain non-inverting, so I'm going to use the non-inverting configuration, which is just a voltage divider on the output. This is our minus input because we need negative feedback. Our input. And let's go ahead and just draw that. We know that it's going to have a Thevenin equivalent. And we don't know what that is. Does it make a difference? Well, no, since the current going into an ideal op-amp, this isn't an ideal op-amp, this is an LF411, but it's pretty close to ideal, is effectively 0. We don't get any voltage drop across this resistor, so even if it's 10K or even 100K, we're not going to get any significant voltage drop, so the V in is going to be the same as the voltage in the source. Now, we need a gain of 100. That means that we need a 99:1 ratio, because we want this to be 1/100th of this voltage, and these voltages are going to be proportional. Well, we don't have a 99:1, but we have a 100K and a 1K. So that's going to give us a gain of 101. That's a 1% error. That's good enough in this class since we accept up to a 10% error. There's not much you can do about it. There's no way with our standard resistors to get exactly 99:1. 100:1 is as good as we're going to get. So V out equals 101 times V in. Not bad. No input current, so we don't care about the source resistance. Our output can go up to 15 volts and down to minus 15 volts. Notice that that means the input is limited to 15 millivolts, plus minus 15 millivolts. 10 times that would be 150. No, sorry, it's plus minus 150 millivolts because that would allow us 15 volts max. All right, let's take a look at the next page. What's the input impedance according to the golden rules? Well, we already talked about that. I in is equal to 0, so V in over I in is equal to infinity. So we effectively have an infinite input impedance. What's the approximate output impedance of your amplifier? Well, the op amp has some internal output resistance, but the negative feedback still tries to keep the output of the op amp at 101 times the input, even as we pull current out of the output. We pull some current out of here. There's a voltage drop internally, but this point is being kept at 101 times. So the output impedance is approximately 0 ohms. Might be in the milliohm range. Finally, according to the golden rules, what's the voltage difference between the two op amp terminals? Well, according to the voltage rules, the op amp keeps V plus equal to V minus. So V plus minus V minus is equal to 0 volts. Now that can't be right. We know that that's approximation. How do we know that's an approximation? Well, the output of the op amp is A times V plus minus V minus. If V plus minus V minus is 0, doesn't make a difference what A is, the output's going to be 0 volts. But then we wouldn't have an amplifier because no matter what we put into it, the output would be 0 volts. The reality is that there has to be some small voltage difference between the two inputs to keep the output at the voltage we want. So let's go ahead and calculate what that needs to be. So we know that V out is equal to the gain of the op amp. In this case, it's pretty low, 10,000, times V plus minus V minus. But we also know that V minus is equal to V out times 1K over 1K plus 100K. That's the voltage divider we used here. That's equal to V out over 101, or V out is equal to 101 times V minus. It's just using algebra. So now let's substitute. We've got 101 times V minus is equal to 10,000. Oops, comma's in the wrong place. V plus minus V minus. That's equal to 10,000 times V plus minus 10,000 times V minus. We now gather terms. We end up with V minus is equal to 10,000 plus 101 equal to 10,000 times V plus. And we end up with 10,101 times V minus is equal to 10,000 times V plus, or V minus is equal to 10,000 over 10,101 V plus. So we can see that V minus is a little bit smaller than V plus, which it has to be because we're going to multiply the difference between those two times 10,000 to get the output. So if V plus is equal to 0.1 volt, V minus is equal to, where did my calculator go? So we got 0.1 volt times 10,000 divided by 10,101 equals 0.099 volts, 99 millivolts. And that says that V plus minus V minus is approximately equal to 1 millivolt. 1 volt, 0.1 volt minus 0.099 volts. And that makes sense because we're going to multiply that by 10,000 to get 100 times 0.1, because our V in is 0.1 volt. If we multiply that by 100, or 101, the output voltage is going to be 10.1 volts, and we need 1 millivolt divided by the open loop gain of the op amp is about 10 volts. So we don't actually have 0 volts difference between V plus and V minus. We have about 1 millivolt, which is pretty small, and it's the reason we say that V plus and V minus are effectively the same thing. Now, the thing to note is that the gain error in the non-inverting amplifier was 1, it was A over 1 plus A. But when we use some of the gain in the amplifier, A, to get gain in the closed loop circuit, in this case we got a gain of 101, we have less gain to reduce the error. And of course the error is the difference between the inputs, V plus and V minus, and the output impedance. So the higher the gain of the closed loop circuit, the higher the errors in the circuit. That doesn't make much difference at DC, but as we get higher frequencies going into the amplifier, the open loop gain decreases. And for example, the LF411 only has an open loop gain of 1 at 4 megahertz. So first of all, there's no way you're going to get a gain of 10 or 100 out of the closed loop circuit if the open loop gain is only 1. The open loop gain has to be at least 100 to get a gain of 100. But also it means the errors are quite large. So this circuit works really well at low frequencies. As we get to higher frequencies, we have to start thinking about whether it's going to work as well. We'll talk about these errors in the next lesson.